Okay, we're going to start pretty simple. We have a crate, because we love crates. Okay, crate is on wheels for a frictionless surface that has mass m. It experiences an applied force in that direction. So if it, now mind you, it has other forces on there, right? It's got normal, it's got mg, but this applied force is going to be our net force, and we result in this is going to have an acceleration. Yeah? Okay. So what we've had so far is we know that our force, net force, is going to equal our mass times acceleration. But as we talked about last time, you know, our acceleration is really what? It's our time derivative with respect to velocity. So this is going to equal our mass times dv dt, right? Yeah. Okay, well, mass, because mass is generally a constant, okay, we can move it inside and out of our operator here to give us our net force is going to equal ddt of mass times, I'm sorry, those should be vectors up there, of our mass times our, you know, our time derivative of mass times our velocity vector. Now, usually our mass is a constant, but we had some, yesterday we talked about some examples where mass would not necessarily be a constant. Jets and rockets, when they're, you know, the whole purpose of it is to spew mass out the back of the engine to propel your device forward. Or the fire hose that is strong enough to knock firemen over, right? Okay, and so we angle it up to keep the normal force back into the ground to increase their force of friction. Because generally you're working on wet ground, right? There's water everywhere at a fire. So they're working on wet ground, they need to increase their force of friction to keep them from sliding around. So if they angle their hose horizontal or even down, then they're going to be struggling with holding onto the hose. Or just staying on the ground for that matter. Okay, so we can usually consider this mass as constant. Well, then this just becomes, and then yesterday we defined this mv is, we've defined it as, okay, as our momentum, which is p. Okay, because m was already taken by mass. So we call it p. There's no other, you're going to love the next one too, by the way. Okay. Now, with this, if this is p, then this whole thing becomes what Newton really said was our second law of, was his second law of motion, was our net force results in a change in our momentum. Okay. Now, the fundamental theorem of calculus, if you guys remember this, tells us that the derivative and the integral are inverse operations of each other, and that, you know, you can go back and forth with that the same way we can go back and forth with multiplication and division. So we can take this dp dt and turn it into a fraction. So this will equal dp dt, and we can treat this dt as a fraction in and of itself. And that's going to give us dp equals the integral of our net force times our time. Okay, the rules of calculus allow this, that we can create this. Well, then if, you know, so if we're integrating this, if we take all of our dp's, this can just become our delta p, right? And so, you know, if we take all of our delta p's, and this is going to become the integral of F net, our net force, times our time differential. Okay, this is going to equal, this here is the cool thing. This is, here I'll move it up. This becomes our change in our momentum. Okay, and so if we experience a force over a period of time, this results in a change in our momentum, and we call this our impulse. Okay, and so impulse is defined as delta p, our change in our momentum, and it has the variable j. Because logically, j would be the variable that we would use for impulse. Right? Current actually is already used, and I, lowercase I, is the symbol for current, and so we picked the next one down the line. We went with j. Maybe there's a Latin thing in there. I don't know, like J in English is written as an I in Latin. Okay, if you watched your Indiana Jones and the Holy Grail, he spells Jehovah with a J, when in Latin it's spelled with an I, and he almost falls to his death. Okay, that's how I remember that. Okay, so there's our J. Okay, and this right here, this idea, this is the impulse momentum theorem. Okay, now, we've seen this sort of thing before, and we know that whenever we take an integral of a product, this is really just force, times our time, right, that we can graph it. Okay, and if this is our net force over here, and it varies with time, here's our time, and this is our force. And all this under here is going to equal our delta P. Okay, so if we find this, so we can find the area underneath our curve, okay, as we've done so many times in earlier units. The area under our curve is going to equal our impulse. All right, well then we go from here, and then our impulse then is also, you know, delta P, right, is then going to equal P final minus P initial. Okay, and we can convert those into MV final minus MV initial. And that's going to equal the integral of F dot dt. So what we really have is we can find our final velocity, you know, if we experience a certain amount of impulse, right? So we could find the area, you know, give this, you know, we can find our change of velocity if we plug it in here, because that's equal to our F dt. And that's really it for the momentum, the impulse momentum theorem. Okay, it's pretty much that. It's just our change in momentum.